Okay, so we will be going through problem number 14. Let's read problem number 14 from page 19 in the review. Problem says, the figure below shows the region bounded by the graphs of x to the 1/2 plus y to the 1/2 equals 2, x equals 0, x equals 1, and the x-axis. So you see the region here. Now, if you think about this equation, you probably wouldn't know what that equation looks like off the top of your head, but that's not a concern here because you're given the graph and very clearly you're given the region. Now, it says find the area of the region. So, I would say the best thing to do here would be to use a dx. Why would we want to use a dx? Because the upper boundary of the region is always the curve and the lower boundary is always the x-axis. However, if you chose to use a dy, you would have two different regions where you would have to do two different integrals. So I would recommend using a dx. Alright, so first, area of the region. Remember, area of the region is just taking the integral of the height of the dx with respect to x. So the height of the dx is just the upper boundary of the region, which is the curve, minus the lower boundary of the region, which is 0. So the curve, it's x to the 1/2 plus y to the 1/2 equals 2. However, this does not work. If we're going to use a dx, we need to have the equation in y equals form. So if I solve for y, how would I do that? Well, I would subtract x to the 1/2, and then how do I get rid of the 1/2 power? I square both sides. So 2 minus x to the 1/2 quantity squared is the value of y. So we're going to take the upper boundary of the dx, which is 2 minus x to the 1/2, that quantity squared minus the lower boundary, which is just the x-axis, or y equals 0. Now, we want to integrate from left to right because we are integrating with respect to x. So, the value on the left is 0. The value on the right is x equals 1. So, we're integrating from 0 to 1, the quantity 2 minus x to the 1/2 squared. Now, it does say find the area, so we do need to carry this out. So our strategy for carrying this integral out is to multiply out 2 minus x to the 1/2 squared. So that would mean, remember, 2 minus x to the 1/2 times itself, 2 minus x to the 1/2. So 2 times 2 is 4, 2 times minus x to the 1/2, and another minus 2 times x to the 1/2 gives us minus 4 x to the 1/2, and then plus x to the 1/2 times 1/2. What do you do with those powers? You add 1/2 and 1/2 together to get x to the first. So we're going to integrate 4 minus 4x to the 1/2 plus x with respect to x. Alright, so the integral of 4 is 4x minus 4 times the integral of x to the 1/2. What is the integral of x to the 1/2? That is x to the 3/2 divided by 3/2, or multiplied by 2/3, and then plus the integral of x, which is x squared over 2, evaluated from 0 to 1. Notice what I've been saying all along is that the numbers that you're going to plug in are actually very simple numbers, 0 to 1, right? So now when we plug in, we get 4 times 1 minus, this would have been 8/3 times 1 to the 3/2 plus 1 squared over 2, and then minus, here would be 4 times 0 minus 8/3 times 0 to the 3/2 plus 0 squared over 2. So of course the second thing is 0. So here I have 4 minus 8/3 times 1, well, it's just 1, and then plus 1/2. So now a common denominator is 6. So 6 over 6, 2 over 2, and 3 over 3. So I'm going to get 24 over 6 minus 16 over 6 plus 3 over 6. So together, 24 minus 16 is 8, plus 3 is 11/6. So now you can see that carrying out the integral, not too bad. Setting up the graph, Well, not bad at all because you're given that, and plugging in the numbers is relatively simple, so no big deal. All right, so our answer is 11/6 for part A. Moving on to part B. So now in part B, it says set up but do not integrate an integral expression in terms of a single variable for the volume of the solid formed by revolving the region around the x-axis. All right, so I'm going to redraw the picture here, but you still have it. So now I have this region, and now we would like to revolve it around the x-axis. So if I revolve around the x-axis, and once again, I should still continue to use a dx. So now I have the dx, right? And the region is bordering the x-axis. So that means my rectangle is perpendicular to the axis of rotation, and we are bordering it, so we should use the disk method. All right, so now the disk method, the setup is, remember, pi times the integral of radius squared with respect to x. All right, so now I'm integrating from left to right, so 0 to 1 still. And then I would like to integrate the radius squared. So the radius is the upper boundary, which is the curve, minus the lower boundary, which is 0. So once again, the curve is what? Well, the curve is the quantity 2 minus x to the 1/2 quantity squared. So remember, problem B says set up but do not integrate. In that scenario, you should set up but do not try to simplify, do not try to do anything. Leave it as is. Now, the answer that I have on the answer sheet is very similar. Pi is on the inside, so 0 to 1, pi times, and then it has the quantity 2 minus root x, quantity squared, I believe, is the answer that I have on the answer sheet, which is the same, and x to the 1/2 would be just fine. But remember, if this is a multiple choice, you would want to make sure that you recognize that x to the 1/2 is the same as root x, and pi on the outside is the same as pi on the inside, as long as it's multiplied by the quantity. So that is part B. All right, moving on to part C. Once again, set up but do not integrate an integral expression in terms of a single variable for the volume of the solid formed by revolving the region around the line x equals 1. So I'm going to redraw the region, which is here, and then it says to revolve around the line x equals 1. Now, x equals 1 is a border of the region, but because I had been using a dx, and I'm going to continue to use a dx, I am using a line that is parallel to the dx, and so now I'm going to use the shell method to find this volume. So I don't really care that the region is being bordered by the axis of rotation. So the setup for the shell method, remember, is 2 pi times the integral of the radius times the height with respect to x. So now, if I'm integrating with respect to x, the limits of integration are still going to be 0 to 1. And now I'm thinking about the radius. All right, so now the radius. Remember, the rectangle, any given rectangle, is x units away from the y-axis. So therefore, the axis of rotation that is 1 unit from the y-axis is 1 minus x units away from the rectangle. So the radius is 1 minus x. Remember, you always take the right-hand thing minus the left-hand thing. So the axis of rotation is 1, so it is on the right of the rectangle, so 1 minus x. Now the height. The height of the dx is the upper boundary of the dx minus the lower boundary. So once again, the upper boundary is the curve, which is the 2 minus x to the 1/2 quantity squared minus the lower boundary once again, which is just 0. So our setup is 2 pi times the integral from 0 to 1 times the radius, which is 1 minus x, times the height, which is 2 minus x to the 1/2 quantity squared. So this is letter C. Once again, it says set up, but do not integrate. So 14 is a great example of a free response question. So just to go back. So if you were looking at this as a free response question, going back to A, this would probably be worth 3 points. The setup is, generally speaking, pretty easy. The integral, relatively easy. Plugging in, relatively easy. So this would be worth 3 points. You'd probably get 1 point for the setup, 1 point for integrating correctly, and then 1 point for plugging into the definite integral, getting 11/6. Moving on to B, what would you get here? Well, you would probably get 1 point for having the limits and the constants. So that would be 0 and 1 and pi. 1 point for having the correct integrand, 2 minus x to the 1/2 squared, and then 1 point for having the squared on the outside. And then in C, once again, set up. Once again, so we have 1 point for the limits, 0 to 1, and the constant, the 2 pi, 1 point for the radius, and 1 point for the height. So 9 points for this free response question.